So we are into the second half of this unit where we are seeing the different types of feedback amplifiers in detail. So yesterday we have seen one amplifier voltage series feedback, and we have derived how the input resistance is going to increase and how the output resistance is going to decrease. So we have, from the equivalent circuit of the voltage series feedback amplifier, we have proved the 2 points mathematically. So theoretically, we have known that when you have voltage series feedback, the input resistance will increase and output resistance will decrease. So that we have proved it using the circuit theory. So now we'll take up current series feedback. So the second type of feedback, and current series feedback amplifier is also called as trans conductance amplifier. So you will see the term GM being used here. And current series output side, I have current, so you will have current source. Input side, I have series, so you will have voltage source. So I told you the shortcut how to identify what will come in the input and output side. In the first term, this current indicates the output side. So in the output, you will have a current source. And the current source value is GM into VA. And whenever you have a current source, you will be having a parallel resistance R0. R0 is the output resistance of your amplifier. And additionally, you are connecting your load RL. So this is your output side. Input side, you see, since you have the term series, input side, so definitely you will have voltage source in series. You will have this RS here. I am clubbing that RS along with RI. So you will have voltage source with RI. RI is your input impedance of your amplifier, and the feedback signal is in series with your input. So two things, series means two things you have to understand. First one, voltage source in series with resistance, you have to draw at the input side. Second thing, you have to mix your voltage, mix your feedback signal in series. And the feedback signal is given by, for current series feedback, see the table yesterday. We have seen the table, current series feedback, the beta is VF by I naught. So VF will be equal to beta into I naught cross multiply. So you should be remembering the beta expression for all the types of feedback amplifiers. We are seeing current series feedback here, okay? So beta value is given by VF by I naught cross multiply VF equal to beta into I naught. So this will be coming in the input side. VF equal to beta into I naught, and the input voltage which is going to your amplifier is Vi. The current entering your amplifier is Ii. The current coming out of your amplifier is I naught. And across RL you measure V naught, and V naught polarity is this plus minus. Across the load resistance you are going to measure the output voltage. See, we can say from this configuration, current series feedback. So input side is series. So definitely the input impedance will increase. Output side is also, I am going to sample current. Current will be same in series. So output resistance will also increase. So here we are going to we will know what we are going to prove. So we are going to prove RIF is going to increase. We are going to prove R0F is going to increase. So that is the main objective of current series feedback. See, remember, voltage series feedback is a voltage amplifier. So we'll be having the voltage gain AV. Current series amplifier is a trans conductance amplifier. So we'll be having GM. Okay, GM is your trans conductance. And see here, this circuit diagram is actually these two are connected, and here you will be having the ground. So don't think they're isolated, they're connected, and you will be having a common ground here. Okay, so that is how the circuit diagram looks like. And the input side, you see, you are having Thevenin's model because you have the term series. Output side, you have Norton's current model because you have the term current. Okay, so that